Steel is made with fire. It always has been. Fire so hot it liquefies rock. It produces more carbon dioxide than almost every country on Earth. Only China and the United States emit more. But in 2013, something changed. We figured out how to make steel without fire. Your phone was designed by algorithms. Your car was assembled by robots. The satellite that tells you where you are was launched on explosions calculated to 17 decimal places. And the steel in all of it, bridges, railways, ships, the rebar inside every building, was made the same way it was made in 1300. Researchers had theorized an alternative for decades. In 2013, MET proved one of them could actually work. And you've probably never heard of it. You just need electricity. That's it. But to understand why that's such a big deal, you need to understand what electricity is actually replacing. This is iron ore. It looks like rock because it is rock. Reddish, heavy, dull. The iron inside is not buried in there like a coin in a jar. It is chemically bonded to oxygen. Iron and oxygen are locked together so completely that you cannot dig it up and melt it. You have to break a chemical bond. You have to divorce the iron from the oxygen. And that divorce is what has defined metallurgy for 3,000 years. Someone discovered that if you built a fire hot enough and packed the right kind of rock around it, something remarkable happened. Metal appeared, liquid, glowing, heavy, pooling at the bottom of the fire pit. Medieval craftsmen scaled the early furnace into the first blast furnaces. The Industrial Revolution multiplied them across continents, but the fundamental transaction never changed. You give fire carbon. Carbon steals oxygen from the ore. You get metal. You get carbon dioxide. Every sword, every bridge, every railway, every skyscraper. 3,000 years, the same deal. Nobody questioned whether it was necessary. Nobody had proven a way around it. The modern version is the blast furnace, 12, 15, sometimes 20 stories tall. They run continuous 24 hours a day for years without stopping. You cannot turn them off. The thermal mass alone would crack the structure. Some have been burning without interruption for over a decade. The heat inside is so intense it is visible from miles away at night. An orange glow on the horizon that people in steel towns have lived beside their entire lives without thinking much about what it means. Iron ore goes in the top. Coke, which is coal stripped down to a near pure carbon skeleton, goes in with it. Air blasted in at nearly 1,200 degrees Celsius ignites the coke. It releases carbon monoxide, which rises and reacts with the iron oxide. The oxygen gets stripped away, liquid metal falls to the bottom, carbon dioxide rises out of the top, millions of tons of it per plant, per year. Here is what matters, that carbon dioxide is not from powering the furnace, it is from the chemistry. Carbon is not just the fuel, it is the reactant. Without carbon, the oxygen goes nowhere, the metal stays locked in the rock. You can swap energy sources, but unless you change the reaction itself, the carbon dioxide problem stays. The steel industry produced 1.9 billion tons of steel in 2024. Making it generated around 4.1 billion tons of carbon dioxide equivalent, roughly 7 to 8% of global greenhouse gas emissions. For 200 years, we assumed that was just the price of metal. That assumption rested on something nobody stopped to question. What is actually holding the iron and oxygen together? Not heat, not pressure. Electrical charge. At its core, this is not a heat problem, it is a bond problem. Iron oxide is held together by electromagnetic attraction. The iron atoms carry a positive charge, the oxygen atoms carry a negative charge. When you run a blast furnace, you're using carbon monoxide as a chemical crowbar, a molecule so hungry for oxygen that it steals oxygen away from the iron. That works. It has always worked. But it produces carbon dioxide when the crowbar does the job. Here is the insight. If the bond is electrical, you do not need a chemical crowbar. You can use electricity directly. Apply a current and the charged particles move on their own. Oxygen goes one way, iron goes the other, no intermediate chemistry, no carbon dioxide. Here is an analogy. Take ordinary table salt, sodium and chlorine locked together. Melt it, drop 2 electrodes in, run a current and the bond breaks. sodium metal pools at one end, chlorine gas bubbles off the other. Not because you added a chemical, but because you applied electricity to something held together by electrical attraction. This is not hypothetical, it is how sodium metal has been produced industrially for over a century. That is electrolysis. The environment for iron is far more extreme. Liquid rock at 1,600 degrees instead of molten salt, but the logic is identical. In 2013, MIT proved it works on iron oxide. The process is called molten oxide electrolysis. You melt the ore electrically, it becomes a liquid mineral soup, extremely hot, extremely reactive, electrically conductive. You run a direct current through it. The positive electrode draws the oxygen out, it bubbles off the surface as pure oxygen gas, visible, physical, gone. Watch it happen in the lab and it looks almost unremarkable. Small bubbles rising through glowing liquid. No roar, no flame, no column of exhaust climbing into the sky, just bubbles. The negative electrode draws the iron. It pools at the bottom silently in liquid metal. The heat comes from the electricity itself. The current that splits the bond also heats the melt. No combustion required. In a blast furnace, ore goes in, metal comes out, carbon dioxide goes into the atmosphere. In molten oxide electrolysis, ore goes in, metal comes out, oxygen goes into the atmosphere. A different byproduct, a different century. Hydrogen-based reduction is also being pursued, and it is currently ahead commercially, with plants already delivering hydrogen-reduced steel to manufacturers. But hydrogen still uses chemistry to remove oxygen. Molten oxide electrolysis skips chemistry entirely. If hydrogen reduction is a cleaner version of the old logic, molten oxide electrolysis is a different logic altogether. To understand how we got here, you need to know about Donald Sadoway. Sadoway is a materials scientist at the MIT. He spent roughly 16 years teaching the university's introductory solid-state chemistry course, hundreds of students at a time and eventually over half the freshman class in a single section. Bill Gates came across the lectures through the MIT OpenCourseWare initiative and emailed Sadoway directly to ask for a meeting and to discuss the research. Sadoway initially ignored the message, assuming his account had been hacked by pranksters at the MIT. It was not. Gates called his lectures the best chemistry lessons anywhere, but teaching was not the work. The work was electrochemistry, what electricity can do to materials that heat alone cannot. His earlier research focused on liquid metal batteries, grid-scale energy storage built from layers of molten metal and salt. That work gave him an intuition most metallurgists did not have, that separating metals from their ores was fundamentally an electrochemical problem, not a thermal one. The insight sounds simple in hindsight. It was not. For a century, the assumption in steelmaking research was that decarbonizing the process meant finding a cleaner source of heat or a cleaner reducing agent. Sadoway's group asked a different question. What if you did not need a reducing agent at all? That question led to years of work on a problem that sounds deceptively simple. What do you make the electrodes out of? At 1,600 degrees, submerged in liquid rock, almost every material dissolves. Steel corrodes, platinum corrodes, graphite oxidizes. The electrode has to conduct current, survive the melt, and not contaminate the metal pooling below it, simultaneously and indefinitely. Earlier work had shown that iridium could do it. Iridium is one of the rarest elements on Earth, rarer than platinum, produced as a byproduct of mining South African platinum ore, extracted in quantities measured in tons per year globally. You could build an iridium anode. You could not build an industry on one. The 2013 Nature paper solved the harder problem. Sadoway's group found that a chromium-based alloy, cheap and abundant and the kind of material used in stainless steel, could survive the conditions of iron oxide electrolysis. When submerged in the melt, a thin protective layer of chromium and aluminum oxide forms spontaneously on its surface. Thick enough to resist the environment, thin enough for current to pass through. The alloy essentially shields itself. That was the breakthrough. Not proof that molten oxide electrolysis worked in principle. Proof that it could be built from materials that actually exist in the world in sufficient quantity. Boston Metal had been founded the year before, in 2012, spun directly out of Sardaway's lab. The technology at that point existed at the scale of a coffee cup, a few grams of metal, a proof of concept. Tadeu Carneiro joined as Chief Executive Officer in 2017, not from the tech world, but from the steel industry itself. He had spent nearly 3 decades at CBMM, the world's largest producer of niobium, a decade of that as its Chief Executive Officer. He understood the industry's conservatism, its deep resistance to change, and exactly why it needed to change anyway. Under Carneiro, Boston Metal raised over $420 million. ArcelorMittal, one of the world's largest steelmakers, invested. So did Vale, the Brazilian mining giant. When the people who run the incumbent industry bet on its own disruption, that is a signal worth paying attention to. The engineering work proceeded in stages: semi-industrial cell in 2014, then years of anode testing, refractory development, current density optimization. Every step up in scale is a new experiment. The melt behaves differently than the models predict. The anode degrades in unexpected ways. Every failure was data. In March 2025, Boston Metal commissioned a multi-inert anode industrial cell at its facility in Woburn, Massachusetts. The outside of the reactor is unremarkable: insulated steel, heavy cable runs, instrumentation panels. Inside, behind refractory walls built from magnesium oxide ceramic, liquid rock glows white at 1,600 degrees Celsius. No flame, no exhaust stack, no smoke, just a low electrical roar, and at the bottom of the cell, pooling slowly, silently, liquid iron. Tonnage scale metal from a single cell without combustion. That is not a commercial plant. It is not displacing a blast furnace. But it is proof that the anode survives, that the cell runs continuously, that the output is real. The question now is whether the next step can happen fast enough to matter. 3 barriers stand between here and there. They are not equal. Power. At commercial scale, electrolysis needs roughly 3 to 5 megawatt hours per ton. Scaled across 1.9 billion tons a year, the total electricity demand would be several times the combined annual consumption of every country in Europe. The process is only as clean as the grid it runs on. The grid is not there yet. Cost. Coking coal is cheap. The blast furnaces running today were built decades ago, their capital costs long since paid off. Electrolysis cells are expensive to build. The refractory linings degrade, and the cost per ton is not competitive yet. That gap is closing. It has not closed. Both of those are engineering problems. Solvable, given time and investment. The third barrier is different in kind. A blast furnace is not just a machine. It is the centre of gravity for everything built around it: coal mines, coking plants, rail lines, port infrastructure, and generations of workers. In Linz, Austria, Voestalpine built its first blast furnaces in the early 1940s, rebuilt them after the war, and has been running them ever since. In Duisburg, Germany, ThyssenKrupp's steel operations are the economic foundation of a region. In Gary, Indiana, and Pittsburgh, Pennsylvania, generations of families built their lives around the rhythms of the furnace. These workers did not design the system they work in. They showed up to jobs that were already there. The pension, the union contract, the local economy, all of it organised around the assumption that the furnace keeps running. Asking them to transition is not swapping one machine for another. It is pulling the floor out while people are standing on it. There is no clean answer here. Move too fast and you devastate communities. Move too slow and you lose the climate. The technology transition and the human transition have to happen together. One without the other fails. And every year that takes, billions more tons of carbon dioxide go into the atmosphere. The pressure is building from the outside. Europe moved first. On January 1st, 2026, the EU Carbon Border Adjustment Mechanism entered its definitive phase. The first time in history that a carbon price has been enforced at a border. Every ton of steel imported into the EU now carries a cost tied directly to its emissions intensity. Countries that built their steel industries on coal are watching that choice become a trade penalty in every market that follows Europe's lead. China is the central question. It produces roughly 55% of the world's steel, more than 1 billion tons a year, and its industry is overwhelmingly blast furnace based, overwhelmingly coal dependent. China has set a carbon neutrality target of 2060 and has announced its own emissions trading system. But the gap between declared targets and operational reality in Chinese heavy industry remains wide. What China does with its steel industry over the next decade will matter more for the global climate than what any other country does. It is not a supporting character in this story, it is the main variable. The decision that may matter most right now, however, is happening in India. A draft of India's national steel policy, reviewed in April 2026, lays out a plan to expand crude steel capacity from 168 million tonnes to 400 million by 2035. Plants are being designed right now. Emissions profiles are being locked in for decades. A blast furnace commissioned this year runs until 2070. Whatever India builds at this moment, it builds for half a century. Here is what is actually at stake. A single large offshore wind turbine requires around 3,000 tonnes of steel, tower, nacelle and the massive foundation driven into the seabed. The transmission towers carrying power across continents, the frames of electric vehicles, the racking of utility-scale solar, all of it is steel. The physical skeleton of the clean energy transition is made of the same material that has always been made with fire, and making it is one of the largest sources of CO2 on the planet. Whoever learns to produce it without carbon, at scale, at cost, does not just win a trade advantage. They become the foundry of the energy transition itself. The limitation is not the technology. The electrons do what they are supposed to do. The limitation is the system built around coal, institutions, supply chains, trade relationships and political dependencies, so entrenched that changing them is not a technical problem. It is a structural one. That system will change. Carbon pricing is accelerating it. Procurement policy is pulling it. The economics are closing in from every direction. But it will not change on its own, and it will not change overnight. For 3,000 years, the price of metal was carbon. We just found out it does not have to be. Now comes the harder part, making a civilization catch up to what a laboratory already knows.